As the eclipse ended, Kilauea did something it hasn't done in weeks, and the timing has people asking questions scientists can actually answer. On August 12, 2026, millions of people across Greenland, Iceland, and northern Spain watched the sky go dark in the middle of the afternoon. A total solar eclipse swept along a narrow path across the Arctic, down through the glaciers and lava fields of Iceland, and finally across the river valleys of northern Spain before slipping out over the Mediterranean. For a brief window, lasting less than 2 minutes in most places along that path, the moon lined up perfectly between the Earth and the sun, and day turned to a strange silver twilight. It was the kind of event that draws eclipse chasers from every continent, and this one was especially rare. The first total solar eclipse visible from Reykjavik since the year 1433. On the very same day, on the opposite side of the planet, something else was stirring. At the summit of Kilauea, one of the most active volcanoes on Earth, monitoring stations run by the United States Geological Survey picked up the first signs of renewed activity. Just after 11 in the morning, Hawaii time, intermittent lava, fountaining, and overflows began at the north vent inside Halema-Uma'u crater. A second overflow followed shortly after. Ground deformation instruments showed the summit inflating, a sign that magma was pushing upward and pressure was building. Within hours, the Hawaiian Volcano Observatory raised Kilauea's alert level from advisory to watch, and its aviation color code from yellow to orange, a formal signal that a new eruptive episode, the 53rd in an ongoing sequence, was imminent. Two major headline-grabbing geological events on opposite sides of the globe, unfolding within hours of each other on the exact day of a total solar eclipse. It's the kind of coincidence that practically writes its own headline. And to be fair, it is genuinely striking, the sort of thing that makes you pause and wonder whether there's more going on beneath the surface than simple chance. Social media picked up on it almost immediately, with clips of Kilauea's glowing fountains circulating alongside footage of the darkened sky over Reykjavik, the pairing implying, without quite saying it outright, that one event had somehow set off the other. So let's actually dig into it, because the honest answer is more interesting than either extreme, more interesting than dismissing it outright, and more interesting than assuming the two events are secretly connected. Start with what was actually happening at Kilauea, because the volcano itself has a story that stretches back long before this particular eclipse. Kilauea sits on the southeastern side of the big island of Hawaii, one of a chain of volcanoes formed as the Pacific tectonic plate slides slowly over a fixed hotspot of rising magma deep in the Earth's mantle. Unlike Cascadia or the San Andreas, this isn't a fault line grinding along a plate boundary. It's a hotspot volcano fed by a more or less constant supply of magma rising from far below the crust, which makes Kilauea one of the most continuously active volcanoes on the planet. It has been erupting, on and off, for essentially its entire recorded history, and for much of the past few years, that activity has centered on the Halema-Uma'u crater at its summit, inside Hawaii Volcanoes National Park. Since this particular eruptive sequence began, Kilauea has gone through dozens of distinct episodes, each one following a strikingly similar pattern. Magma slowly accumulates beneath the summit, causing the ground to inflate, sometimes measurably, over days or weeks. Eventually, pressure builds to the point where lava breaks through at one of the summit vents, producing intense fountains that can shoot hundreds of feet into the air. One earlier episode in this same sequence sent a fountain roughly 500 feet skyward and produced an ash plume that reached nearly 19,000 feet above sea level. Then, often within hours, the episode ends abruptly, the fountaining stops, and the volcano goes quiet again while magma resupplies beneath the surface, setting up the next cycle. This isn't random behavior, it's a rhythm, driven by the mechanics of magma supply and pressure. Release, and scientists at the observatory have gotten good enough at reading the signs, ground tilt, gas emissions, seismic tremor, that they can often forecast, with real precision, when the next episode is likely to begin, sometimes narrowing the window down to a span of just a few days. That's exactly what was happening in the lead up to August 12th. In the days before, monitoring instruments recorded the telltale deflation and inflation cycles that typically precede a new episode. The observatory had already published a forecast window, estimating that episode 53 was likely sometime between August 13th and 17th. When the precursory fountaining began slightly ahead of that window on the 12th, it wasn't a surprise to the scientists watching the data. It was the volcano doing almost exactly what its own recent history predicted it would do, on a timeline that had been narrowing for days, independent of anything happening in the sky. To put that forecasting precision in perspective, it's worth remembering how unusual it is in the broader world of natural hazards to be able to predict a major geological event within a 5-day window at all. Earthquakes remain essentially unpredictable on any specific timescale, and even the most sophisticated models for a fault like Cascadia can only offer probability estimates spanning decades. Kilauea's summit eruptions are a rare exception, precisely because this particular volcanic system produces such clear, repeatable warning signs. The magma supply feeding Halemaumau comes from a relatively shallow, well-monitored reservoir, and each fountaining episode drains that reservoir enough to trigger a measurable, trackable refill period before the next one. Scientists have been recording this exact cycle, episode after episode, for long enough now that the pattern itself has become one of the more reliable short-term eruption forecasts anywhere on the planet. That reliability is also part of why this particular story lends itself so easily to a false sense of cosmic timing. The eruption really was extremely well-timed, just not by anything happening in the sky. It was timed by a volcano whose own internal rhythm had been logged, episode by episode, for months. That last point matters, because it cuts against the idea that the eclipse somehow triggered the eruption. If a celestial alignment thousands of miles away, over an entirely different tectonic setting, were the deciding factor in when Kilauea's magma finally broke through, you'd expect the volcano's own internal signals, the inflation, the tremor, the gas readings, to look erratic or disconnected from the actual eruption timing. Instead, they lined up almost perfectly with the pattern the volcano had already been following for months. The eruption looks, in every measurable way, like Kilauea simply continuing to do what Kilauea does, on a schedule set by magma supply rather than by the position of the moon. So why does the coincidence still feel significant? Partly, it's a matter of scale and rarity bias. A total solar eclipse feels enormous and singular, the kind of event most people experience once or twice in a lifetime, so anything that happens to coincide with it feels charged with meaning. But volcanic eruptions, globally, are far more common than most people realize. At any given moment, researchers who track this kind of activity estimate that somewhere between 20 and 50 volcanoes are erupting somewhere on Earth. That's not a typo. It's the normal ongoing background state of the planet. Databases that catalog this activity list dozens of volcanoes with continuing eruption status in any given year, and out of those, roughly 20 tend to be actively erupting on any particular day, whether or not anyone happens to be watching a celestial event at the same time. The days surrounding this particular eclipse make that baseline easy to see in action. Sicily's Etna has had explosive activity multiple times in the days surrounding this eclipse, with fresh vents opening on its eastern flank and satellite imagery tracking lava flows across the mountainside. Stromboli, one of the most continuously active volcanoes in the world, was producing intense explosions and lava overflows in the same window, part of a pattern of activity so constant that the volcano has earned the nickname Lighthouse of the Mediterranean for the way it glows through the night, essentially every night, regardless of the calendar. Guatemala's Volcán de Fuego went through a dangerous explosive phase that forced the evacuation of more than 1,000 people just days before the eclipse. None of these were caused by the eclipse either. They're simply what a geologically active planet looks like on any given week. Given that baseline, the real surprise wouldn't have been a volcano erupting around the time of a major eclipse. It would have been if nothing anywhere on Earth had been erupting at all. There's a similar story unfolding on the other side of the globe, in the exact region where the eclipse's path of totality actually passed. Iceland's Reykjanes Peninsula, just outside Reykjavik, has been going through its own extended eruptive sequence since the very end of 2023. 9 separate eruptions have broken out along the Sundanukur crater row near the town of Grindavik, some lasting just hours, others continuing for weeks, and reshaping the surrounding landscape with fresh lava fields. The most recent of these ran through the middle of last summer before ending in early August. Since then, geologists monitoring the area have continued to track slow ground uplift around the nearby Svartsengi region, the unmistakable signature of magma quietly refilling underground, the same pattern that has preceded every eruption in this cycle so far. Icelandic scientists have been saying for weeks, independent of the eclipse entirely, that conditions on the peninsula looked primed for another eruption, simply because the magma chamber was approaching the pressure levels that triggered previous events. That set up an almost irresistible narrative for anyone watching the eclipse from Iceland. The possibility of standing on the Reykjanes Peninsula, inside the path of totality, and potentially witnessing both a total solar eclipse and an active volcanic eruption in the same frame. Tour companies leaned into it, some explicitly advertising the chance to see fresh lava alongside totality. Local guides were candid about the odds. An eruption was plausible, even likely at some point in the coming weeks, but not because of the eclipse. It was likely because the region has been geologically restless for years, with or without anything happening in the sky. If Reykjanes does erupt again in the days surrounding this eclipse, it will be joining Kilauea as another case of a volcano behaving exactly as its own internal magma cycle predicted, at a moment when the whole world happened to be looking upward instead of down. Which brings us to the more interesting question underneath all of this. Is there any real physical mechanism by which an eclipse could actually influence volcanic or seismic activity? It's not an unreasonable question to ask, and it's one scientists have actually studied directly, rather than simply dismissing. During a solar eclipse, the sun and moon align almost perfectly from Earth's perspective, in a configuration astronomers call syzygy. That same alignment happens less dramatically during every new moon, and it does have a real measurable effect. It slightly increases the combined gravitational pull on Earth, producing what are called spring tides. The extra strong ocean tides you may have noticed happen around new and full moons. Because a total solar eclipse always occurs during a new moon, by definition, that same modest boost in tidal stress is present. Researchers have spent decades investigating whether these small, regular increases in tidal stress can nudge already stressed faults or already pressurized magma chambers into rupturing slightly earlier than they otherwise would have. The findings, across dozens of studies on this exact question, are underwhelming in a scientifically important way. The effect, where it's detectable at all, is tiny, generally limited to systems that are already right on the edge of failure, and nowhere close to strong enough to be described as triggering an eruption or an earthquake in any meaningful sense on its own. There's also been direct, dedicated research specifically on solar eclipses and seismic activity, prompted by the exact kind of speculation this story invites. Following the total solar eclipse that crossed North America in April 2024, a seismologist and planetary scientist at Johns Hopkins University led a study specifically investigating whether the celestial event had produced any detectable ground-shaking effect. The results, presented at the Seismological Society of America's annual meeting, did find a real seismic signature tied to the eclipse, but not the kind anyone expected. Rather than any tectonic effect, what the instruments picked up was a dramatic, temporary drop in the everyday background vibration that comes from ordinary human activity. Traffic easing off the roads, factories and machinery pausing, entire communities stopping to look up at the sky. As millions of people paused what they were doing to watch totality, the Earth, in a very literal sense, briefly grew. Quieter, not because of any planetary alignment shaking the ground, but because people stopped moving around on top of it. The researcher leading that study later described noticing the same eerie calm firsthand, watching totality from Ohio, and realizing that what he was sensing wasn't some cosmic hush settling over the landscape. It was simply everyone around him stopping in place at the same moment. It's a genuinely elegant finding, and it directly undercuts the idea that eclipses generate meaningful geological disturbances. If anything, the data suggests the opposite, a moment of stillness, both human and seismic. This particular myth, the idea that eclipses trigger earthquakes or eruptions, has proven remarkably persistent, resurfacing almost every time a major eclipse crosses a populated part of the world. Researchers who study public perception of natural hazards have pointed out that the myth tends to spread hardest in the days immediately surrounding an eclipse, precisely when people are primed to notice any dramatic geological news and mentally file it under related. It rarely survives contact with the actual data, but by the time scientists have had a chance to check the records and publish a rebuttal, the eclipse has usually already passed, and public attention has already moved on to the next thing. That timing lag is part of why the myth keeps circulating decade after decade, even though the underlying science has been reasonably well settled for a long time. It's worth being precise about what the science does and doesn't rule out, because the honest picture is a little more nuanced than a flat, no connection whatsoever. Earth tides, the same gravitational flexing that produces ocean tides, do measurably deform solid rock, not just water. And that deformation has been documented in extremely sensitive strain measurements around active fault zones and volcanic systems worldwide. Some studies looking at very large data sets spanning many years and many separate volcanic systems have found statistically detectable, if small, upticks in eruptive activity clustering loosely around the times of new and full moons when tidal stress peaks. Other studies looking at the same broad question have failed to find any significant correlation at all, and the ones that do find an effect consistently describe it as a subtle nudge, only relevant for a magma chamber or fault that was already sitting right at the threshold of failure, primed to go regardless. In other words, tidal stress might occasionally act as something like a final tiny push on a system that was already fully loaded and ready to give way on its own, not a trigger capable of starting an eruption or an earthquake in a system that wasn't already there. Kilauea, days out from its own internally forecast eruption window, and Reykjanes, months into an independently documented magma refilling cycle, both look like systems that were already there, running on their own clocks, with or without an eclipse overhead. So where does that leave the coincidence between the eclipse and Kilauea's newest episode? Sitting most likely exactly where it appears to sit. Two independent natural systems, one driven by orbital mechanics on a timescale of months and years, the other driven by magma supply on a timescale of days and weeks, happening to land on the same calendar date. It's a genuinely fun coincidence, the kind of thing that makes for a great photo if you happen to be standing in the right spot in Iceland watching lava glow on the horizon during totality. But happen to align in time and one cause the other are very different claims, and the evidence here points clearly toward the former. That distinction matters beyond just this one story because it's part of a much older, much broader pattern in how people relate to natural disasters. Humans are pattern-seeking by nature. It's a trait that has served us well for most of our evolutionary history, helping us notice real, useful correlations in the world around us. But that same instinct can misfire when it comes to genuinely rare, dramatic, low-frequency events like eclipses and major eruptions, where the human brain is primed to search for a connective thread, even when the underlying systems are entirely unrelated. Throughout history, cultures across the world have linked eclipses to floods, famines, wars, and the deaths of kings, not because those connections held up under scrutiny, but because the eclipse was memorable, and memorable events attract explanations, even invented ones. Modern versions of the same instinct show up constantly online, particularly whenever a widely watched celestial event lines up with any kind of dramatic geological news. It doesn't take malicious intent to spread, just the very human tendency to notice a coincidence and reach for a story that makes it feel meaningful. None of this is to say Kilauea's eruption isn't worth paying attention to in its own right. It very much is, just not because of the sky. Episode 53 is part of a genuinely significant ongoing eruptive sequence that has already reshaped parts of the summit caldera, produced ash plumes tall enough to require aviation advisories, and repeatedly closed sections of Hawaii Volcanoes National Park for public safety. The crater rim around Halemaumau has been closed to visitors since 2007, specifically because of the instability these kinds of eruptions produce, cracking, slumping ground, and the risk of sudden rockfalls exposing molten material beneath the surface. Scientists at the observatory continue to monitor tilt, gas output, and seismic tremor around the clock, refining their forecasts with each new episode, building an increasingly detailed picture of exactly how this particular volcano behaves. That's the real story here. Not a mysterious cosmic trigger, but a well-instrumented, closely studied volcanic system doing something scientists can actually track, explain, and with real precision, anticipate. The same goes for Reykjanes. If another eruption does break out on the peninsula in the days around this eclipse, it won't be evidence of some hidden celestial influence. It will be evidence of a magma chamber that has been slowly refilling for months. Following a pattern, local geologists have already mapped out through 9 previous eruptions in the same sequence. For residents of the region, and for the Icelandic authorities managing road closures and visitor safety around Grindavik, that pattern is far more useful than any speculation about the eclipse, because it's the pattern that actually predicts what happens next. There's something worth sitting with in that distinction. The instinct to connect an eclipse and an eruption comes from the same place as genuine scientific curiosity, a desire to understand how the pieces of a complicated planet fit together. The difference is what happens after that initial spark of curiosity. Real Earth science follows it with instruments, with decades of ground truth data, with careful studies specifically designed to test whether a suspected connection actually holds up under scrutiny, the kind of study that, in this case, keeps coming back with the same answer. These are separate systems, operating on separate physical principles, and the fact that they occasionally share a calendar date says more about the size of the planet's ongoing volcanic activity than it does about any hidden link between the sun, the moon, and the fire beneath our feet. It also says something about how these stories travel once they leave the hands of the scientists who actually study them. A measured, carefully hedged research finding, tidal stress can, under specific and narrow conditions, marginally influence the timing of an eruption that was already primed to happen. Doesn't translate cleanly into a headline. Somewhere in the retelling, the careful conditions tend to fall away, and what's left is a much simpler, much more dramatic claim. The eclipse triggered the eruption. That simplified version spreads faster, gets more attention, and is considerably harder to correct once it's out in the world, which is part of why myths like this one keep resurfacing generation after generation, essentially unchanged. Regardless of how many times researchers publish work directly addressing them, none of that makes the actual events any less worth watching closely. Quite the opposite. Kilauea's eruptive sequence has been one of the most closely monitored volcanic events in recent memory, generating a steady stream of publicly available data. Tilt measurements, gas emission rates, seismic tremor logs, live camera feeds from the crater rim that anyone can follow in close to real time. The Reykjanes eruptions have similarly turned a stretch of Icelandic coastline into one of the best documented volcanic systems on Earth, with each of the 9 eruptions in the sequence adding another data point to scientists' understanding of exactly how magma accumulates and breaks through in that particular setting. Both are genuinely remarkable geological stories, full of real drama, real hazard, and real scientific insight. They simply don't need an eclipse to make them significant. The volcano was already the story. So when the fountains at Kaolauia reached full height, hours after the moon's shadow had already swept across Iceland and out over the Atlantic, it wasn't the eclipse reaching down into the earth. It was a volcano finishing a cycle it had already been building toward for days, on a planet that, at any given moment, is quietly erupting somewhere. The eclipse gave millions of people a reason to look up. Kaolauia, on its own schedule, gave a much smaller number of people watching a very different set of instruments a reason to look down. Both were spectacular. Neither one caused the other. And once you understand why, the coincidence doesn't get less interesting. If anything, it gets more interesting, because now you know exactly what you're actually looking at. 2 entirely different clocks inside the same planet, both simply keeping their own time,